So it might have been a while since you've gone through the discussion of tangent lines. So I thought it would be good to back up a little bit and look at that. So we'll just do it by example. Suppose we've got the exponential function. So this guy looks, if you look at its power series, it's going to be the one that has x to the n over n factorial. So the first few terms of that are 1, and then x squared over 2, and then x cubed over 3 factorial, and so on and so forth, right? So if we do a little sketch of this guy, so here's the x-axis, and here's my vertical axis, y equals fx. And the exponential function looks something like that. So there's e to the x. And suppose we want to look at the tangent line at 0. So at this point right here, so here's the point 0, 1. And then the tangent line is going to be what we get from just taking the first part, the 0th and first terms of that series, and it's going to be this one right here. So this is 1 plus x. Okay, so the equation comes from y minus the particular y0, and here we're using x0 as 0 and y0 as 1. And then this is going to be equal to, now the slope is going to be given by the value of the derivative at this point, because that's what a derivative does or is. And then we have the x displacement. Okay, so rewriting that for this example, y minus 1 is equal to, and then we've got e to the 0 times x minus 0. And then cleaning that up a little bit, we've got y minus 1 is equal to x, or y equals 1 plus x. Okay, and so there's our blue line. All right, so now we're going to translate this into something for more variables. So if we have z equals f of xy. So here f is a function from R2 into R. Then the tangent plane is going to be something that looks very similar to this formula that we started with over here, only in a multivariable version. So on the left side, we have the vertical value, so z minus the particular z naught that we're at is equal to, and then on the right, we need to have the slope going in the x direction, so that's the partial with respect to x, evaluated at this point, times the x displacement. But then there's also the slope moving in the y direction, so partial with respect to y, evaluated at this point, times the y displacement. Okay. And then the linear approximation is going to be given by, and so now we just use this idea of translating between these two to reinterpret what's going on here as being values of f. So we say f of xy is equal to, and then on the right side we move z naught over, where it becomes f of x naught y naught, plus, and then we add that to what was already there in the first place, right? Now the only thing is, this is no longer the formula for f, because as soon as we start to vary x from x naught and y from y naught, it's going to be different, just in exactly the same way that there's a discrepancy as soon as we move from either side over here on the one dimensional or one variable case. So that means that we have to replace this equality with an approximation. So this is the linear approximation to f.